All right, guys, today we're going to talk about types of random variables. First of all, a random variable is a numerical outcome of a random process. Now, the random process could be a bunch of different things. We're going to look at those in just a minute, but the key here is that it is a numerical outcome. So to be a random variable, it has to be a numerical outcome of a given random process. So the first one that we're going to talk about is a discrete random variable. And a discrete random variable is a random variable which has a countable number of possible outcomes. So a discrete random variable is a random variable which has a countable number of possible outcomes. So that means we could look at it and actually count it. 1, 2, 3, 4, 5. The other kind that we're going to talk about is a continuous random variable. A continuous random variable is a random variable that can assume any value on a continuous segment of the real number line. That means we have infinitely many values. It's not countable. We couldn't sit there and say 1, 2, 3. We're going to include decimals, fractions, all of that good junk. Now, an easy way to discern between these two is that discrete is counted and continuous is measured. So discrete random variables are counted, continuous random variables are measured. Continuous can have fractions and decimals. Discrete is very, very distinct between each other. So for 1 through 10, it says classify each of the following as either a discrete random variable or a continuous random variable. Again, the easiest way to discern between the two, discrete is counted, continuous is measured. So number 1, it says the number of pages in a standard math textbook. So you have to ask yourself, do we count those or do we measure those? And since we can count the number in a math textbook, they're numbered, that would be discrete. Number 2, the amount of electricity used daily in a home, that is measured. They measure that, so that is continuous, because one house could use like 125.5, another house could use 125.51. I don't really know what that's measured in, but you guys get the picture. On number 3, the number of customers entering a restaurant in one day, that would be able to be counted, so that would be discrete. Number 4, the time spent daily on the phone after supper by a teenager. So you have to ask yourself, would you count how long they spend on the phone or would you measure how long they spend on the phone? Well, if you're timing something, that would be measured, that would be continuous. Number 5, campers at a state park over Labor Day weekend. Campers are people. You cannot have half of a person. You would count that. That would be discrete. So what I'd like you to do now is pause the video and do number 6 through 10. All right, on number 6, the number of phone calls received in a day is discrete. 7, the speed of pitches of Major League softball pitchers would be speed that's measured, that's continuous. Number 8, the weight of a lobster caught in Maine, that's measured, so that's continuous. Number 9, the number of defective circuits on a computer chip is counted, so that's discrete. And then number 10, the time it takes for a 5-year battery to die would be measured, that's continuous. So that's a good way to discern between discrete and continuous. Can you count it or do you have to measure it? Now that we understand the difference between those, let's talk about how to describe a discrete random variable. There are 3 steps that you need to follow to describe a discrete random variable. Step 1 is you have to state the variable. Step 2, you have to list all the possible values of that variable. And step 3 is you need to determine the possibilities of these values. So when defining a random variable, capital letters such as X will be used to refer to the random variable. Lowercase letters, such as little x over here, will refer to the specific values of the random variable. Now that's a little confusing, so let's look at this example. Example, if we're going to toss a coin, we could get either heads or tails. So to make this a random variable, it has to have a numerical outcome. If you guys will remember from the top of your page, random variable has to have a numerical outcome. So I'm going to give the value of getting or tossing a head would be 0 and give the value of tossing a tails to be 1. Therefore, now that we've made it numerical, we have random value or random variable capital X. So this random variable X right here represents tossing a coin. That's what the X represents. Now the possible values that we could get, heads or tails, since we made them numerical, those represent the specific values. So another way we could write that is we could say lowercase x sub 1 equals 0 and lowercase x sub 2 equals 1. That means that lowercase x would represent getting heads and lowercase x2 would represent getting tails. Okay, so those are my random events. So state the variable, list all the possible values, that would be this right here, and then determine the possibility of these values. Now the possibility would kind of be like the probability, we talked about that in the past. And then finally, we could choose whatever number we wanted to represent heads or tails. They chose 0 and 1 because that makes the most sense to us, it's the most basic, but we could choose 100 and 150, whatever. The only thing we could not choose is like H to represent heads or T to represent tails, because H and T are not numeric. In order for this to be a random variable, it has to be numeric. So you couldn't say H and T, you couldn't say red and blue, you couldn't say top and bottom, you would have to give it a numerical value. Now, another important thing to discern between is that a random variable, this capital X that represents like the toss of a coin, is different than an algebraic variable. In algebra, we can solve for the value of x. Like if I gave you this equation, you could subtract 1 and you would know that x equals 1. That's not the same as a random variable. A random variable is a whole set of values. So the random variable for tossing a coin is 0 and 1. That's the random variable. So it could be 0 and 1, it could be 1, 2, 3. That is what a random variable is, and it could take on any of those values randomly, hence the name random variable. On the back side, we've got a couple of examples for you guys to get a hang of this. So on number 11, it says we're going to toss a 6-sided die and observe the outcome of the toss. So part A says identify the random variable. So we're going to identify the random variable as a capital X, and we have to say what X represents. What does it describe? Well, it describes this whole situation, which is the outcome of the toss of a die. Okay. Now the range of values are all the possibilities that you could get back. So the range of values, we're going to have our capital X equals, and we're going to show a set bracket here because it's a set of values and it could be any of them randomly. So when I toss a 6-sided die, what are the possibilities that I could get back? I could roll a 1, I could roll a 2, I could roll a 3, I could roll a 4, I could roll a 5, or I could roll a 6. So the range of values is 1 through 6, and you can see here that my capital X equals, and that's kind of like what we had on the front side here, where the capital X equals my possible values of 0 and 1. Now that is not the only way you could write that. You could also come over here and you could say, okay, x sub 1 equals 1, that's my first possible outcome. X sub 2 equals 2, that's my second possible outcome. X sub 3 equals 3, that's my third possible outcome, all the way to x sub 6 equals 6. Now if you're going to do it that way, something that you should be aware of is this number has no relation to this number. X sub 1 does not equal 1 because 1 and 1. That's just saying this is the first outcome that I looked at. So I could put x1 equals 6, x2 equals 5, x3 equals 4. Those numbers have no relation whatsoever. Finally, on part C, I want to come up with a probability distribution. I want to know what's the probability of each one of these possible outcomes. So I'm going to make a T-chart here. And on the left side, we're going to have lowercase x. That's representing all of my possible outcomes. My possible outcomes are 1, 2, 3, 4, 5, and 6. On the right side here, I want to know what's the probability that my random variable could be that outcome. So capital X equals lowercase x. So what's the probability that my random variable would equal 1? Well, I have 1 out of 6 to get that because I have 6 possible values. Okay, well what's the probability that my random variable is going to be a 2? Well, that's only one number out of 6. Probability that my random value is going to be a 3, that's 1 out of 6, 4 is 1 out of 6, 5 is 1 out of 6, and 6 is 1 out of 6. And the reason that we know that is from last unit where we talked about rolling a die. It's 6-sided, it's even, you have 1 in 6 chance of rolling any of those numbers. Number 12, the number of defective integrated circuits received in a batch of 1,000. So identify the random variable, so that's going to be a capital X equals, and that's going to represent the number, the whole situation here, the number of defective circuits in a batch of 1,000. Now, the range of values is going to be a little different here. So we're still going to have x equals, I'm going to have the set brackets, but if we have a set of, or a batch of 1,000 integrated circuits, and I want to know how many of them are defective, you got to think, we might not have any defective circuits. There might be a batch of 1,000 perfect ones. We could have one defective circuit, we could have two defective circuits, we could have three defective circuits, but I don't want to list all of those numbers. I could literally have all the way up to however many I have. So I'm going to put dot, dot, dot. I could have 1,000 defective circuits here. Okay, I could have 1,000. Now, again, if you wanted to write those like we were talking about above, this would be a little bit different. My first possible outcome would be 0. I could have 0. My second possible outcome would be 1. And I would go all the way up to, now this is a little bit different because how many circuits would I have here? What possible outcome would this be? And that would be my 1,001 possible outcome would be 1,000. Now the probability distribution for this guy is a little bit different because they didn't give us any information. They didn't tell me like 10% of the batches are typically defective. They didn't give me any numbers that I could kind of go with. They don't know if there's like an equal chance. This is where things are different. This is an unknown probability distribution. Now, if they gave us previous data, we could probably go back and figure out like what the probability of pulling a defective circuit would be, but at this point we do not know. On number 13, it says the head nurse of the pediatric division of the Sisters of Mercy Hospital is trying to determine the capacity requirement for the nursery. She realizes that the number of babies born at the hospital each day is a random variable. So, first thing, identify the random variable. What is she trying to figure out? She's trying to figure out the number of babies born each day at that specific hospital. So I'm going to say the number of babies born at Sisters of Mercy Hospital. Oh, not Hobbs, hospital. Each day. Now the range of values is going to be different on this one because we don't have an end game. We know where we can start, but we don't know how many are going to be born. They might have a slow day, they might have a very busy day. Is this in a small town like Ellis or Hayes, or is this in a huge town like New York City? So the range of values is going to be hard to describe. What we do know about it is that it has to be a whole number. We can't have half of a baby be born. So we know that it's going to be a whole number. And we know that it has to be greater than 0. Like we could have no babies born that day, but we don't know, like, do they stop at 3? Is the max number of babies they can hold 100? We don't know. So we're going to say whole numbers from 0 to some large positive number. Okay, that's going to be my range of values. Now, probability distribution, again, they didn't give us any previous information. We know nothing about this, so this is going to be unknown. This is definitely something, though, that we could go back at the Sisters of Mercy Hospital and we could look into their records and get an average and figure out from there, figure out the probability. But since they didn't give us any of that information, we are unable to move forward with that. On number 14, it says a local restaurant has an express policy that states that lunch will be served within 15 minutes of ordering or it will be free. Obviously, the restaurant is keenly interested in not giving away its product and in delivering on its promise of a timely lunch. But the length of time to prepare each meal varies because of the difference in preparation times of each dish, the load on the kitchen, and the experience of the chefs and the waitresses. Since time is measured on a continuous scale and the variability of meal preparation is not predictable, the time between ordering and receiving a meal is considered to be a continuous random variable. So be careful. Take note. This guy right here is continuous. Okay, this is measured. 15 minutes is their limit. So this is measured. This is continuous. So to identify the random variable, what are we wanting to take note of here? And that would be the time between ordering a meal and receiving it. That's what we're measuring. The time between ordering a meal and receiving it. Now the range of values is different. We know that like the fastest they could get it out there would be instantaneous. So we could start at 0 minutes, but we don't know, like we know we want them to get it before 15 minutes, but the meal could take longer than that, so it could go all the way up to infinity. What if someone waited there for like eternity to get their meal, even though sometimes it feels like it. But something to note that's very important here is that this has to be on a continuous scale. On a continuous scale. And then finally, the probability distribution. They didn't give us any values, anything that we can measure to figure this out. So again, this is going to be unknown. You could look at previous data if they collected it, if they measured in the past, but I don't know a restaurant that typically does that unless you're like at the drive-thru at Taco Bell.